This is a fundamentally important curve in nuclear physics, okay? Remember that binding energy per nucleon is a measure of the potential energy. These guys are actually, because they're so tightly bound, this is the lowest nuclear potential energy. Okay, that's the lowest potential energy there, okay? So in a nuclear reaction, in our fission reactors and our fission nuclear bombs, right, we are basically releasing this much energy per nucleon. There's 238 nucleons there, right? Okay, so if we split uranium and make things like iron, okay, every nucleon we release about that much MeVs of energy, right? So binding energy per nucleon is your binding energy divided by your mass number, okay? Notice that, by the way, if we fuse things, if we join the nuclei, that's what this side is, right? Okay. If we fuse them, that's a whole lot more energy, right? This is a bigger change, right? This is why a hydrogen bomb is so much more powerful than a fission bomb, okay? Yeah, so it's like they measure equivalents of TNT. Fission bombs are kilotons of TNT. These guys are megatons of TNT, the hydrogen bombs, right? So if you really want to kill people, you really want a hydrogen bomb. So if we look at the physics of this, right, this is the most tightly bound. This is fission, so splitting molecules apart, creating fissures in them, right? Okay. This is where fission releases energy. This is where fusion releases energy. Okay. Now, basically, in our universe, stars are doing this. Stars are causing nuclear fusion. Okay, there's heat and pressure in the core of the star, and they're fusing hydrogen. Right now, our sun is making hydrogen into helium. I don't know that our sun is big enough. I think it will do some helium into like carbon, right? But supergiant stars will go all the way up this. At the very end, they're going to be fusing things like carbon, doing carbon fusion and making things like iron. Okay, so this is fusion. In their normal life, they will do fusion, and there's stages of life. So hydrogen fusion, helium fusion, carbon fusion, et cetera, et cetera. Carbon fusion, by the way, those are the white dwarfs, incredibly hot, right? Okay, so then the question is, where do these heavy things come from? Those come from when you have you have a degenerate matter. And degenerate matter is just protons and electrons and neutrons and electrons, all the atomic constituents, just cheek and jowl, no space between them, right? That's very dense, but it can be more dense. Okay, so a supernova is when something the size basically of the planet Earth collapses to something about the size of Portland. Okay, this is a tremendous release of energy, and basically the electrons get stuffed into the protons, and we get neutrons. This is totally neutrons. Okay, that's a neutron star, and that's where these things come from. Okay, there's a crust of these heavier elements on that. And the fact that we have these in planet Earth means that we're made of the debris of a supergiant star collapse. Sorry, I'm going off into astrophysics, but these come from a supernova and nuclear reactors, right? Okay. So yeah, so nuclear fission is splitting nuclei. Fusion is joining them. This is a typical fission reaction. We already looked at this one, right? Nuclear fusion for the sun, there's something called the proton-proton cycle. And it's complicated, and there's neutrinos and stuff involved. But the basic idea here is that we're turning hydrogen into helium, okay? The next step, by the way, is that we can make carbon. So helium fusion can make carbon. Supergiant stars can make things as big as magnesium, silicon. We can go, all these guys can fuse and make things like iron, okay? But those are supergiant stars that can do that, okay? This is a type of question that they like to put on the test. And it's basically a nuclear reaction. We're going to go left side, right side, but we're going to have to use binding energy per nucleon, right? Now keep in mind that the binding energy of an atom, okay, is the binding energy per nucleon multiplied by the number of nucleons, right? So this is the mass number, right? This is our binding energy. Binding energy per nucleon is what's actually being graphed here. Okay, and we have to multiply that. I'll show you. We have to multiply that by the mass number to actually get the binding energy. And then the difference in binding energy simply is the energy released. It's pretty simple then. Okay, so let's look at this. They're saying 2 deuterium atoms fuse to make 2 heliums, right? So let's go with it. So 2, 1, that's deuterium, right? 2, 1, and we're going to make a 4, 2. Looks good, right? We're all good. All these numbers add up. We're all good, right? Okay. Now let's look this up. This guy is, I'm going to say this is 1.1 MeV per nucleon. And then notice that helium is somewhat more tightly bound. That's why we're releasing energy. We're releasing per nucleon all this energy, right? So let's figure out. This is 7.1 MeV per nucleon. A lot of ways to do this. By the way, we have 4 nucleons in play here, but let's do it this way. Okay. So to figure out the binding energy of deuterium, I'm going to go 2. This is very rough numbers here, okay? So 2 times, because there's 2 nucleons, right? Times 1.1 MeV per nucleon, right? Okay, and then the binding energy of this guy is 2 times 1.1. These are MeVs, right? MeVs per nucleon. And then that's going to become this guy. This is 4 nucleons. You see that? Because it's 4 there. And then look at that number is 7.1, right? It's more tightly bound. Remember that this is low potential energy. This is high potential energy. It's sort of a backwards graph, okay? Because remember, binding energy is not energy you have. It's energy you would have to put in to tear it apart. So let's do some math here. This is 4.4, and this is 28.4. Right? So the change in energy is 24 MeV. Right? Total change in energy is 24 MeV. So we're supposed to show that it's 4 picojoules, right? A picojoule, these are in your data packet. Pico is 10 to the minus 12th. Right, just like picofarads was 10 to the minus 12th farads. So let's show 24 times 10 to the 6th. Remember, that's MeV, that's mega, right? That is EV. And then we have to turn that into joules. Times 10 to the minus 19th. I know they only give you 1.60, but, you know, I've just memorized it. So, all right, fine. Okay, so 24 E6 times 1.602 E minus 19 is 3.8 times 10 to the minus 12th. You love that, right? Joules, right? Which is about 4 picojoules, because 10 to the minus 12th joules is what it is, right? Okay. And then let me just show you another example of a question that they give you, right? It's like, oh, there it is, right? Well, where's the peak of this, right? Nickel, we've got that. It's like we got to draw this graph, right? Well, nickel is right at the peak there, right? So how do we draw this graph? Oh, I don't even know. It's like, and then it's like, yeah, something like that, right? You want the top of it to be there, right? So that's not even that good, right? It's like, and then you've got like a zigzaggedy thing here, right? I don't know, right? How good did I do? Not real good. Okay. Anyway, I'm going to stop talking there. I think there's some other examples there, right?